Okay, guys. Let's continue with our discussions of duality. So today we're going to be talking about duality in general, for general programs. We're going to actually even talk about some things that would apply to non-convex problems today. So we're going to just think about generic optimization problems, although as per the theme we've seen so far, we can say a lot more about convex ones. So we're going to pay special attention to them. Oh, and just I guess as a quick reminder, your project proposals, the milestone 1, I believe, is due this evening. So make sure that you remember to submit that. Okay, so last time we talked about duality in linear programs, and we saw this in various forms, but here was one form that was the most general. If you have a linear program of this form, minimize C transpose X, subject to AX equals B, and GX less than or equal to H. So this describes, this could describe any linear program. Then we saw that we could construct another linear program that we called its dual. And in the context of the relationship between this program on the left-hand side and the right-hand side, we call this one the primal. And that dual, it had a bunch of interesting features. Okay, some of them were that this was a minimization problem that we started with. It was a linear program. Its dual ends up being a maximization problem that's also a linear program. The variables in this linear program, we have one variable per constraint in the original primal linear program. Okay, so if I had, I would assign essentially one component of U as an example to every equality constraint here, and one component of V to every inequality constraint. And that explains the dimensions of U and V. And the last interesting and important property was that the maximum value of this linear program, by construction, we construct it to be less than or equal to the minimum value of this linear program. So if we started with this linear program and we wanted to get a lower bound on its criterion value, solving this maximization problem we saw would do so, and in fact it would give us the tightest lower bound out of our construction possible. That's why we had a max here. So here was the explanation we gave last time. We started off doing this for very simple linear programs with, just like two variables, but we moved on to something of this form. But in any case, it was constructive. We were constructing these lower bounds, I think, in a very intuitive way. And we started off by saying that if you took any feasible x, so that means any x that satisfies these constraints, any u and any v that's non-negative in every component, then u transpose ax minus b plus v transpose gx minus h must be less than or equal to 0. Why? Because at feasibility, this is 0, so this whole term is 0. This is going to be less than or equal to 0 in every component. This is bigger than or equal to 0 in every component. So if I take their inner product, I get something that's less than or equal to 0. Okay, that was as simple as the fact that we used primal feasibility and a signed restriction for v. And we could rearrange that to look like something transpose x is bigger than or equal to something else. Okay, that something ends up being minus A transpose U minus G transpose V. That something else ends up being minus B transpose U minus H transpose V. And we observed that if we happen to make this equal to C, then this would give us a lower bound on our original problem, because the criterion is exactly C transpose X. And so we've just proved that for any feasible X for which this is equal to C, the primal criterion is bigger than or equal to minus B transpose U minus H transpose V. Okay, so that was the way we constructed this lower bound. And to get the tightest lower bound possible, right, we maximize this over all possible U and V that meet the constraints that we specified so far, which was that V has to be bigger than or equal to 0 in every component, and C has to be equal to this quantity here. That gives us the dual linear program. Yeah? Yeah, that's just a typo. So that should say V. Thanks. Okay, so this was our explanation for LP duality. here was the second explanation. Okay, and you're going to see why somehow the second explanation is important to have. Before we give it, let me just let's think through what would happen if we tried the same strategy, but we had a nonlinear criterion. Okay, what happens if I tried the same strategy and my criterion was not a linear function of x, like it was a quadratic function? Okay, I could form this statement. This is always true, right? This has nothing to do with the criterion. This is just feasibility, which has to do with the constraints, and it had to do with the fact that we took v to be bigger than or equal to 0. But if my criterion was a quadratic function of x, there would be no way I could rearrange this to get the criterion less than or equal to something. Right? There's no way to take a linear function of x and map it into a quadratic function by simply somehow trying to assign some constraints for u and v. Right? That would not be possible. So it seems like if we're just thinking about constructing duals in this way, or constructing, like, say, lower bounds on the criterion this way, we can't move beyond essentially linearity in the criterion. This is why the second explanation is so important, because it allows us to construct the same dual problem through different arguments that are actually completely general and will allow us to make statements about arbitrary programs. And it's different in a subtle way, but there's an important difference. So the second explanation starts off with a very similar observation, which is that it's in fact the same observation. It's that this is less than or equal to 0, okay, when x is feasible and v is bigger than or equal to 0. And we use that to say that actually the criterion C transpose x is bigger than or equal to C transpose x plus this. Okay, we call this Lagrangian. It's a function of x, our primal variable, and u and v are dual variables. And we observed that if C was this feasible set in the primal, so it's a set of all C for x for which these constraints were met, ax equals b and gx is less than or equal to h, then we could minimize over x and c both sides. Okay, and if we minimize this side over x and c, that's exactly f star. That is the primal optimal value by definition. And we're just writing the minimum of the right-hand side over x and c as min x and c L x uv. That's how we defined the Lagrangian, right? Just to equal this thing. And here's the key step in Lagrangian duality. This itself is bigger than or equal to the unconstrained minimization. Right? If I'm trying to minimize the Lagrangian with u and v fixed over x in some set, it's always lower bounded if I remove the constraints on x. Right? This can only be made smaller if I minimize unconstrained over x. And this thing we call the Lagrange dual function. The reason we make this step is that often this thing is computable in closed form. For lots of nice problems, we can actually compute the unconstrained minimum of the Lagrangian in closed form. So it's really this inequality that is the key to Lagrangian duality. So we defined this function guv, which was just min over x of Lx uv. It's called the Lagrange dual function. And if you went through the calculations, right, if I just tried to minimize this Lagrangian up here, as I've defined in the first line, over x, then I get minus infinity, essentially, if that thing is truly a linear function, which means that the coefficient multiplying x is not 0, right? Because the minimum of a linear function over all x is going to be minus infinity for a proper linear function. And if it actually had a 0 coefficient multiplying x, and it was just a constant function, right, which occurs if c is equal to minus a transpose u minus g transpose v, then the minimum over all x is just that constant. So this is our Lagrange dual function. It's just straightforward calculation for minimizing this thing over x, and maximizing the Lagrange dual function, which is going to give us the tightest lower bound possible, right? Because we've just said that f star is bigger than or equal to gu of v for all u and v, is going to give us the same linear program here. Okay, and we like this because it's completely general. It applies to arbitrary optimization problems. And so we're going to step through this for general optimization problems right now. Let me pause for questions. Yeah.
Are there
a good question. It's a bit of a complicated answer because there are other duals that are named that you might run into, like the Fenchel dual. But I claim that Lagrangian duality is kind of the most general. So once you understand Lagrangian duality, then you get, if you read another dual, like, for example, Fenchel duality, it's a special case of Lagrangian duality. Just like this kind of particular construction for LPs is a special case of Lagrangian duality. So we'll cover conjugate functions in 2 lectures, and then you'll see something that people call Fenchel duality, and we'll see it's really just a special case of Lagrangian duality. Other questions? Okay, so we're going to just go through really these concepts carefully. It's everything I said in the last slide, but just for general problems. I don't actually have a ton of slides today, so I was planning on going through this carefully because it's a very important concept. And we're going to spend the next 2 lectures effectively also on duality. The next lecture is really on the KKT conditions, which transparently are not about duality. They're about optimality, but they're very closely tied. And the lecture after that is on all the uses of duality, so why we care about duals. So that's the plan. And if we end up finishing early today, then I'm happy to let you guys go early because I didn't plan to have a ton of things to say, just really cover duality very carefully today. So let's consider a general optimization problem. And it's going to take this form. Minimize f of x subject to hi of x is less than or equal to 0, and lj of x is equal to 0. And we're not going to, at this point, place any constraints on f, h, and l, hi, and lj. Okay, we're just going to think of these as functions. This is a generic optimization problem, as general as you could make it. Of course, we'll pay special attention to the convex case where f is convex. These hi's are convex, and each of these lj's is an affine function. We'll try to keep things as general as possible. The Lagrangian, as you saw for linear programs, is defined in the analogous way for general problems, which is just start with a criterion, define a dual variable ui for every one of these inequality constraints, vj for every one of these equality constraints, and take the inner product, or the sum of ui hi of x, and the sum of vj lj of x, and add that to the criterion. So that's called the Lagrangian. And for those of you who've seen Lagrange multipliers in calculus or in physics or somewhere else, this is the same thing. This is the same kind of concept. We call these u's and v's dual variables in the context of Lagrange duality, but you might also call them Lagrange multipliers. So we've had new variables been introduced, and in vector form u is in Rm and v is in R. I guess I called the number of equality constraints R. And we're going to restrict u to be bigger than or equal to 0, because we're going to try to get the property that we got before, which is that this thing at feasibility is less than or equal to 0. So we're going to try to constrain u to be bigger than or equal to 0. And one way we can formalize that is just by saying that the Lagrangian has domain, which is over these variables u and v, which is all v, but only u that are bigger than or equal to 0. Or equivalently, we can set it equal to minus infinity if u is less than 0. This should really say in any component, right? If any component of u is less than 0. So there's this important property, which it's just what we saw before. And I'll just say again, almost all of duality in the KKT conditions is not hard math. It's full of very simple observations, but somehow are strung together in a way that gets something very, some very deep conclusions falling out. So this important property is that if we take any feasible x, primal feasible x, any v and any u that's bigger than or equal to 0, then f of x is bigger than or equal to Lagrangian Lx uv. Okay, and the rationale is the same as before. At feasibility, each one of these hi's is less than or equal to 0. This ui is bigger than or equal to 0, right? So this whole thing is less than or equal to 0, this sum. And at feasibility, each one of these lj's is equal to 0, so this whole thing is equal to 0. Right? So by construction, all these sums put together are less than or equal to 0. The Lagrangian is less than or equal to f of x. And so here's a visualization of that. This is an example where f is non-convex. So the solid line here is f. Okay. Suppose our minimization problem is minimize f, which is this solid line, subject to, I have this one function h, which is drawn as a dotted line, being less than or equal to 0. So the feasible set, if I cut the graph of the function h, the feasible set, so the set of all x for which it's less than or equal to 0, is denoted by this interval between these dotted lines. So it's roughly minus 0.5 to 0.5. Okay, so I want to minimize f over this interval. We can see that the minimum occurs at the bound of the interval. This is actually maybe not surprising, because if you look carefully, the function is actually concave on this interval. But in any case, what we're kind of looking to demonstrate here is actually what the Lagrangian looks like, okay, for various choices of the dual variables. So here v is kind of empty. There is no v because there's no equality constraint, so there's really only u. And we can choose a bunch of different positive values of u, let's say, and each one of those positive values traces out a particular dotted curve, which is fix that positive value of u, look at that Lagrangian as a function of x, okay? And as we vary u, we get a bunch of dotted curves, which are shown here. On the feasible set, every one of these dotted curves lies beneath f pointwise. Right? For every x, f of x is bigger than or equal to the Lagrangian at x for all those positive u's. So we're demonstrating this property, right, that we get a pointwise lower bound on f on the feasible set for a bunch of different dual variables u. Outside of the feasible set, in fact, is not true, right? I mean, nothing here would hold if we looked outside the feasible set. And in the simple example, it's exactly the opposite. Because outside the feasible set, we only have one constraint here, right? That's h of x is less than or equal to 0. So outside the feasible set, it's actually bigger than or equal to 0. And so ui times hi of x, or u times h of x, is actually positive, and so it actually upper bounds the function. So it's the opposite in this simple example. But what we're demonstrating is that in the feasible set, we get this property. Okay. So the next thing that we're going to talk about is the Lagrange dual function. Let's suppose that C is the primal feasible set, which we're using for the argument with LPs as well. And let's let f star denote the primal optimal value. Then just taking this inequality here, minimizing out over x and c, gives us the following property. So the left-hand side is the minimum of f of x over x and c. That's f star by definition. The right-hand side is by definition minimum of x in c of Lx uv. And as I've said before, the key part of Lagrange duality, the construction in Lagrange duality, is that we can further lower bound this by removing the constraint on x in this minimization. This is bigger than or equal to the minimum over x of Lx uv. And of course, we could have also stopped here and defined this to be the Lagrange dual function. That would have had the same property. It does lower bound the criterion at every x that's feasible, but it's just not typically computable, right? If you couldn't solve your optimization problem in the first place, why would you be able to solve it if you just added stuff to the criterion? Right? Minimizing over x and c f of x, that is your optimization problem. Presumably that's not trivial because you're studying duality. This is not computable, right? I couldn't tell you what this is, let's say in most interesting cases. Removing all of the constraints, okay, can often simplify the program dramatically. This is often computable, especially with maybe enough manipulations to the problem. In the first place, we could end up with a problem that was equivalent to our original one, such that the minimum of its unconstrained Lagrangian was actually closed form. And that's why we make this step, because this is often computable, and it has the same lower bounding property, right? For every u that's bigger than or equal to 0 and every v, this function guv is less than or equal to f star. Okay, so here was, this is, by the way, called the Lagrange dual function. And here was carrying forward that example that I showed you in the last slide. This dotted line is f star. in this simple problem. Previously, it is the optimal value of our primal problem. Okay, as I varied lambda in this picture, which was Ru, so remember that V was vacuous in this example because there's no equality constraint. I trace out a different number, g of u, and that's called the dual function. This is the Lagrange dual function we're plotting, right, as a function of u. And for every u that's bigger than or equal to 0, so if I continue indefinitely in this way, it's going to lower bound the primal criterion. Okay, and so we're just demonstrating this property. Right. So there's something else interesting happening here that we'll revisit shortly, right? And that is that the best lower bound possible, right, which is this point, is actually not equal to the primal optimal value. So there is a gap here in the sense that if I maximize this over all u and v, that's actually strictly less than f star. So why do you guys think that's happened in this problem? Yeah, so and that's a kind of a philosophical reason that not all inequalities are active here. That's true. But what about this problem in particular maybe is, let's say, abnormal considering our usual course of study? It's not convex. That's actually the important observation is that the primal problem is not convex. So here is empirical proof that for a non-convex problem, we could construct the dual. Here it is. It wasn't hard. But it didn't give us a tight lower bound. In fact, the lower bound on the primal criterion value that's best, right, that's given by maximizing the dual function, is there's a gap between that and the primal criterion. Yeah?
On the previous slide, we're not claiming that converse is true, right? That if L of x is less than f of x, then it's feasible?
Correct. We're not claiming that. That doesn't need to be true, right? Because I could, for example, have some of these constraints violated, but one of them just being very large negative and still retain this, at a particular point x, still retain this inequality. So it's a good observation. Another maybe important thing, or let me pose this as a question rather. In this simple example, we saw if we go outside of the feasible set, we actually get the opposite inequality, right? That L x u v is bigger than f of x. Is that true in general? If I give you a problem and I construct the Lagrangian and I tell you to evaluate outside the primal feasible set, can we say anything in general? We can't, right? Because in this example, we had just one constraint function, so its sign actually flipped, moving outside the feasible set. But in general, you know, I could just be violating one of the constraints, and it could be actually not enough to flip the sign of this, move outside the feasible set. So just another maybe reinforcement or assertion that we're just really claiming that if x is feasible, then this inequality holds. There's not another direction there. Okay, let me give you an example. Oh, there's another question.
So, do we claim to either for convex functions we always get these
We haven't claimed anything yet, but we're going to see at the closer to the end of this lecture that is pretty much always true, except for some fairly pathological convex problems. So let's go through an example where we actually compute the Lagrange dual function. You can get an idea of what it would look like and why it's easier to do than it's easy to do once we drop the constraints. So this is a quadratic program. We've already constructed the Lagrange dual function, by the way, for linear programs. Right, that was here. That was just this calculation. This is the Lagrange dual function for linear programs. So let's move to quadratic programs. Did I call it Q? Yeah. So I chose a standard form QP. Okay, and we're going to assign, did I call it V? we're going to assign a Lagrange dual variable v to every one of these equality constraints and u to every one of these inequality constraints. And we're going to rewrite this as actually minus x is less than or equal to minus 0. And u is going to be constrained to be non-negative in every component, and it's going to really be associated with this constraint, right? Because we think about putting constraints in this form, h I of x is less than or equal to 0. So I just flipped the sign of this constraint. The Lagrangian, literally as we defined it on the last slide, is just a few slides ago, is the primal criterion plus the sum of ui times the inequality constraint functions, which is minus xi, plus the sum of vj times the equality constraint functions. So I can write this as, let's say, something equal to 0, and that something is ai transpose x minus bi, or j. And it's just more concise to write this as minus u transpose x plus v transpose ax minus b. Okay, and we're going to want to minimize this over x, so it's going to help to rearrange so that we get all kind of terms that multiply x as one common term. So I'm just going to take all those terms. So I have c minus u plus a transpose v transpose x, and the only thing left over is minus v transpose b. Okay, and so the first observation, just in the context of this example, was that if I take any u that's bigger than or equal to 0 and any v, this actually lower bounds the optimal value of this problem. So that, though that was constructed through very simple arguments, right, just by observing somehow from this step that ax is going to be equal to b at feasibility, and this is going to be bigger than or equal to 0 at feasibility, so this whole thing should be less than or equal to 0. It's still a non-trivial statement, right? If I gave you this quadratic program, this guy here, and I told you, well, look, I'm going to add to your quadratic part this linear bit. That's going to be always less than or equal to pointwise this criterion. At feasibility, that's still a pretty non-trivial statement. It's not obvious somehow. And we're going to see that the dual actually lower bounds this quadratic program is also non-trivial. It's not an obvious statement. You couldn't look at it transparently and say that was the case. So let's construct the Lagrange dual function, okay, which we're going to get by minimizing this out over all x. So this is just a quadratic, so we could take its gradient, set it equal to 0. And so let's just do a little calculation here. If we take the gradient, set it equal to 0, we get that qx, right, should be equal to c minus u plus a transpose v. Right, and here I suppose it's important to mention that I am assuming that q is strictly positive definite, so it has an inverse. So the solution is just q inverse c minus u plus a transpose v. Right, that is the minimizing x here. And if I were to plug that in, then I'm going to get 1/2 this transpose qx, right, which is going to look like 1/2 c minus u plus a transpose v q inverse q times the same thing. That's this term, 1/2 x transpose qx plus, wait, sorry, I'm missing a sign here. right? If I set the gradient equal to 0, then I say qx is equal to negative this. So I'm missing a sign. So this is actually negative 1/2 times this quantity. This term, c minus u plus a transpose v transpose x, that's just this guy. And I have minus v transpose b, right, that carried through. And so if I look at the first two terms, I have 1/2 times c minus u plus a transpose v q inverse the same quantity. Then I have the same quantity but positive without a half. So the total term I have left is just a half yeah, thank you. So there was two negatives that canceled, one negative doesn't cancel. So it's going to be in total negative 1/2 c minus u plus a transpose v times q inverse c minus u plus a transpose v minus v transpose b. Okay, so that's the Lagrange dual function. Hopefully it matches what we have in the slides. And if you take any u that's bigger than or equal to 0 and any v, that's a lower bound on the primal criterion value at optimum here. Okay, that was just a consequence of our construction. And again, this is a very non-trivial thing to end up with a very simple calculation. It's not at all obvious somehow that this quadratic is actually going to give us a lower bound on this quadratic program. So let me pause and observe that there's a symmetry here, just like there was for LPs. What happens if I were to ask for the tightest lower bound possible? I would maximize this over all u and v, right? And that is actually going to give me another quadratic program. Just like we saw for LPs, its dual was an LP. For QPs, their dual is a QP as well. So there's this very nice symmetry. And that's actually true for SDPs. It's true for conic programs. It's true for a lot of problem classes that the dual is of the same class as the primal. It has a symmetric structure, right? What were variables, so what were constraints somehow in the primal get mapped to variables in the dual. Okay, and so we've just basically, through calculation, saw that was true for LPs and QPs so far. I had a bit more general calculation here, and I suppose maybe we'll just go through it since we have the time, which is what happens if Q is not positive definite but positive semi-definite. So it's just good for you to see such a case, because so let's say it's not necessarily invertible. We're just going to say that it's positive semi-definite. So it could have 0 eigenvalues, in other words. This is still a convex problem, right? But this calculation is not quite as easy. And we're going to see more constraints popping up in the dual. Because somewhat similar to the linear program case, in some circumstances, well, yeah, let's just go through the calculation. You'll see we get more constraints popping up. So we're going to arrive at the same step, which is that we've not used invertibility of Q anywhere up until this point, right, where we're going to minimize the Lagrangian. And so now if we're going to look to minimize the Lagrangian, we do the same thing. We take a derivative of the Lagrangian with respect to x, or a gradient, and we derive it at this equation. But now Q is not invertible. Right? So it's not as simple as saying that x is equal to Q inverse times this quantity. And there's kind of two cases we have to consider. The first case is when minus C minus U plus A transpose V is not in the column space of Q. So Q here is singular, possibly. It could be that this does not lie in the image of Q at all. There is no x for which this equality is true. That's a possibility when Q is singular. In that case, actually, what that means is that if you were to minimize the Lagrangian over x, you get negative infinity. Okay, it's similar to the linear program case. Essentially, in that case, that means there's an x that is going to essentially make this term 0, but make this term arbitrarily large negative in this case. So in this case, the minimum is minus infinity. Okay? If indeed we're in the other case, where this is in the column space of Q, okay, then the minimizer is given by x equals Q pseudo-inverse of this quantity. And in case you've forgotten, this is the generalized inverse of Q, or the pseudo-inverse of Q. What it means is that one way to think about it being defined is that it gives us the minimum 2-norm solution to this linear system. So in the case when Q is singular, and let's say this is in the column space of Q, there are infinitely many solutions. This is the minimum 2-norm solution. That's how this acts, the pseudo-inverse operator. Okay, so this is a solution, and if we plugged it back in, we would get essentially the analogous quantity we got before, just with where we saw Q inverse, it was Q plus. And now we have kind of two cases, right? It's either negative infinity or it's this. And I wrote this thing, C minus U plus A transpose V, orthogonal to the null space of Q. That's actually equivalent to these statements, right? So, for example, if this is in the column space of Q, which means it's in the row space of Q because Q is symmetric, that's equivalent to it being orthogonal to the null space of Q, because the null space and the row space are orthogonal complements for any matrix. Right? So there's another way of expressing the same conditions I wrote down here. Otherwise, it's minus infinity. So this is, in fact, a linear constraint. Okay, we can think of this as a linear constraint. If you gave me a matrix that parameterized the null space of Q, maybe call it M, okay, whose columns were a basis for null space of Q, then this would be equivalent to M times this vector is equal to 0. So it just gives us another constraint in our QP. This just is a linear constraint, essentially. Okay, so maybe it's another helpful fact that the dual of a QP is always a QP, whether or not the quadratic form is strictly positive definite. It's just it either has a simpler or more complicated form with additional equality constraints in the case when Q is non-invertible. So let me give an example, like a pictorial example, and then talk about the dual problem, and then we'll take a quick break. So here's a pictorial example. I chose f to be a quadratic function of two variables, and I had no equality constraints, and I just had the inequality constraint that x has to be bigger than or equal to 0. So x has to lie in the positive orthant in R2. And I did this because, in this case, the dual variable, right, is also quadratic. Well, that's what we actually saw from this derivation. The dual is always a quadratic when the primal is a quadratic. The number of variables it has is the number of primal constraints, but I only had these inequality constraints, so it actually has the same number of variables as the primal, right, if I had no equality constraints. So here in my pictorial example, it's also quadratic in two variables, and it has the same actually constraints. It's u bigger than or equal to 0. It has this nice symmetric structure. That's why I chose kind of this particular primal form. So we can plot it. We can plot them both, in fact, with kind of overloading the axes. So here I'm plotting the primal quadratic as a surface as a function of x1 and x2, right? Both constrained to be bigger than or equal to 0. And here I'm plotting the dual quadratic as a surface as a function of u1 and u2. And again, for its variables, they're both constrained to bigger than or equal to 0 as well. And so we just see visually that we have this property that we had derived, which is that point-wise, this lower bound's the primal optimal value. Okay, so this quadratic is always above this quadratic. And if we look at the minimum of this primal quadratic, that's this red point, that's the minimizer, and this dotted line is the minimum. Okay, this quadratic still occurs, still is less than or equal to that minimizer everywhere. And here's an interesting kind of just empirical observation at this point so far. Two things. The first is that actually the dual is tight. So here, if we maximize the lower bound given by the dual, it does give us back the same dotted line. Okay, that's really no more special than convexity, we're going to see. But here's something else that we can see empirically. The maximizer of the dual actually occurs at the boundary. So it occurs when you, in this case, well, it's hard to tell, but I'll tell you that the primal minimum actually, let's say, occurs in the interior of its constraint set. So I'm going to tell you that the primal minimum actually occurs for strictly positive x1 and x2. And in that case, we can see that the dual maximizer actually occurs at 0, at u1, u2 equal to 0. That's not a coincidence. That's actually that's demonstrating another principle of duality. Can anybody guess what that's called, or does anybody know what that's called? That's just complementary slackness. So we're going to see that's part of the KKT conditions next time. So we can actually learn things about the dual optimum from the primal optimum and vice versa. That is what we're going to learn next time. So this is just an implication of that. It's not like a coincidence empirically. So let me define the Lagrange dual problem, and then we will take a quick break. We've been mentioning it kind of implicitly so far. It's something that we've been mentioning almost with every example we've given, but here is the formal definition. Starting with this problem, we define its Lagrange dual function, as we've done already, to satisfy this inequality for all feasible, we call them dual feasible u and v, which means that u is bigger than or equal to 0 and v is anything. And the Lagrange dual problem maximizes this dual function to get the best lower bound possible. Okay, so it's simply max uv of guv subject to u being bigger than or equal to 0. This possibly hides some domain constraints on G, right? This looks rather simple, but remember, G might be actually negative infinity if certain constraints on U and V don't hold. So that was true here in this quadratic program. That was also true here in this linear program, right? So G maybe implicitly in its domain has a bunch of constraints on U and V. So really the dual problem, this is just masking what may be more constraints that are effectively there. Okay, but there's this key property that holds called weak duality, which is just based on how we constructed this, is that if we were to maximize the dual and get something that we call G star, that's the optimal value of this program, and minimize the primal and get F star, then by construction F star is bigger than or equal to G star. Right? This came from this inequality, just maximizing out over all U and V. This always holds. Weak duality always holds. It's just a property of Lagrange duality. It holds even if the primal problem is non-convex. Nothing to do with convexity. We always get this ordering. Okay, let's take a break there, and we'll come back and tell you a surprising fact about the dual. Okay, guys, let's continue on. Don't worry, I think that was I didn't look at my phone, but I'm pretty sure that was a test. So nothing bad is really happening. So here's another key property of the dual. By the way, this has been hiding. I'll wait a moment so I can get some dramatic effects, because you guys should all hear this property. This is something that's been hiding there all along. We haven't actually said it, but the proof is trivial. The dual problem is always a convex optimization problem. Okay, as written, it's a concave maximization problem. So the claim is that actually G is always concave. Doesn't matter what we started off with. You could have the most pathological convex, non-convex primal. If you go through the calculations, whatever they are, you'll end up with a dual for which this function G is concave. So it's a concave maximization. Remember, we refer to that as convex optimization still, right? Because it's equivalent to minimizing minus g, where minus g is convex. So why is that true? That's true for a very kind of trivial reason. We just are going to use one operation that preserves convexity. So the dual function, by definition, is the minimum of the Lagrangian over all x, right? And that's just equal to f of x plus the sum of ui hi of x plus the sum of vj lj of x. Okay? I'm going to flip the sign and call this minus max of x of minus f of x minus the sum of ui hi of x minus the sum of vj lj of x. Let's look at this thing. Call this thing, okay, I'll just call this thing g sub x of uv. So think of this thing for fixed x as a function of uv only. And you can see the Lagrange dual function g uv is just minus the max of x of these functions g sub x uv. So in other words, it is for each fixed u and v, the maximum over all x. What is this function as a function of u and v? What kind of function is this as a function of u and v? If I look at this function. Yeah, in fact, let's just simply, what is class of function, the smallest class of function you could assign to this? Yeah, it's affine, right? If x fixed x, this is just a bunch of constants multiplying the u's, sum them up. So in fact, this is affine in uv. So if I take the pointwise max of a bunch of affine functions, right? I'm just have a bunch of affine functions in uv, I'm taking their max. That's still going to be a convex function. So this is our max rule. This is convex in uv. Right, because it was convex to begin with. Affine is a very special class within convexity. And I have a negative up front, right? So that means that g is negative something convex. It means it's concave. That's the whole proof. So, right. So let me give you an example of this. Just an example that demonstrates just how surprising it can be. Or maybe not surprising, but just how bizarre it can kind of surface in some ways. I'm starting off with a non-convex primal problem. Okay, I chose a quartic. And you'll see why I chose a quartic shortly. I chose a quartic. Here's the plot of my quartic. X to the 4 minus 50x squared plus 100x. I'm going to minimize this subject to the constraint that x is bigger than or equal to minus 4.5. That's my primal. Okay, this is the constraint. I have to be to the right of this constraint. You can see visually that my primal is not convex. Okay. Before I describe to you the dual function, I'll just mention here was the primal optimal value in red. Here was the dual function, which actually can be constructed in closed form. I'll show you that in the next slide. I mean, it's ugly, but it's still closed form. And we see again the same phenomenon we saw in a previous non-convex example. Maximizing the dual, it does indeed give us something that's less than or equal to the primal optimal value. That is, there's no question of that. That's just weak duality. But there's a gap. Okay, so there's not, we don't get a tight lower bound here. So let me now construct the dual for you. How did I do this? Let me just kind of sketch it out for you in some steps. So the Lagrangian I have just one constraint, right? The constraint is that u is bigger than or equal to minus, or x is bigger than or equal to minus 4.5. So I just have one dual variable u. Okay, just like I only have one primal variable. The Lagrangian is exactly my criterion. And I have u times the constraint that minus x is less than or equal to 4.5. Or in other words, I can write this as minus x minus 4.5 is less than or equal to 0. Right, so I get minus ux minus 4.5u. That's my Lagrangian. Okay. Take a derivative and set this equal to 0 and see where its minimum occurs and see if that minimum is to the right of 4.5, minus 4.5. That's how we can actually, I'm sorry, it has nothing to do with the constraints. I don't know why I said that. We're just minimizing this unconstrained, right? So take a derivative with respect to x. We get something like this. Okay, and just find all of the roots of this cubic. The reason I chose my original function to be a quartic was that there are closed form solutions to roots for a cubic. Right? They're kind of complicated, but they are known. They're named after some Italian mathematician whose name I forget at this point. But they're you can probably Google it, cubic roots. I can look at all the roots, and I can just evaluate the criterion and see which one is smallest. That's how I can minimize this Lagrangian. Like plug in all the roots, just look at which one is actually smallest. So that gives me, once I plug that in, plug in for those roots, define the dual function accordingly, that gives me this, which is complicated. And the details are actually not interesting or important. But what is interesting is that this thing is a concave function of u. Okay? This is an extremely kind of messy function that is concave in u. And if I were to give you this function on a homework and I were to say, prove that it's concave, I would say good luck, because there are no operations that preserve convexity that are obvious here that would reduce this to something that you know. It's just a very exotic function. But by construction, it's concave, right? It is concave because it's a dual function. And it looks like this. So sometimes you might end up at, as I've mentioned several times before, very kind of deep or powerful statements like this one through very simple arguments like this one. And in a case like this simple problem, the concavity of this function is super non-trivial. And it would be very non-obvious unless I knew it was coming out of the Lagrange duality construction. Okay. So now we're going to move to, yes? It's not really an actionable way of proving convexity. It is a way of proving convexity, like in this example, but I don't know instances in which it would be easier to recognize that it was a dual function than it would be to somehow try to use the things. Like if you happen to recognize that, then it is a very powerful property like this one. But I don't know that I would say it's a general purpose tool. Let's put it that way. Lots of non-convex problems, by the way. Let me just mention as an editorial comment. Lots of non-convex problems, they actually have duals that are computable in closed form. Yeah, like this one, but there's several other very non-trivial non-convex problems that have duals that are computable in closed form. And there are lots of instances in which we do get strong duality for non-convex problems. There's some interesting class of non-convex problems for which that occurs. They just tend to be, maybe as kind of per the usual comment, these tend to be more exceptions than the rule. So let's talk about strong duality. We always saw that this held, this is called weak duality, and strong duality was a much kind of stronger case of this, which was actually they're equal. So I've constructed a dual whose criterion at optimum actually matches the primal criterion. That's called strong duality. And you might ask, when does that happen? And we've seen that in LPs it happens quite a bit. I've told you that in convex problems it's pretty much the rule that it happens. And it doesn't happen often in non-convex problems. So here is a condition that is sufficient for strong duality. It's not necessary. Okay, it's just a sufficient condition. There are a bunch of other conditions that are sufficient for strong duality. This is a relatively general and simple one as well. It's called Slater's condition, and the condition is as follows. If the primal is convex, so if it's a convex problem to begin with, and there's at least one strictly feasible x, which means that there's at least one x that satisfies all of the equality constraints, and it strictly satisfies all of the inequality constraints, then you get strong duality. Okay, so this is not saying that at optimum we have these inactive constraints. It's just saying that there is a feasible point, so that if I looked at the interior or the relative interior of the constraint set, right, once I ignore the affine constraints, it's non-empty. That's all it's saying. So it's a very weak condition. It's very pathological that this doesn't happen for convex problems. So you'd have to design pretty odd constraints for that to be the case. And there's an important refinement of Slater's condition, which is kind of obvious if you were to think about what this means for convex problems. Some of these may be affine. Okay, we actually only need strict inequality to hold for the non-affine functions. So if I have affine functions here, I can actually ignore them, and I'm only requiring for the non-affine functions that we can get strict inequalities at one feasible point. I think I saw a hand somewhere. Is there a question? Okay. The proof of this is not difficult. I think that the Boyd and Vandenberg book gives a proof for maybe a special case or a simplified version of this, but it's not a difficult proof, just like everything else with duality. Let's think about what this means for a few cases. Let's think about what this means for LPs. I think this is something instructive. So remember, we have something like this. I guess actually the form of the LP and its dual are not actually that important. And I'm probably going to get it wrong. I'll just read it off from the slide because I'm probably going to get it wrong. But I just want to give you something concrete to look at. So let's think about the primal in the dual, LP. Okay, Slater's condition. Okay, actually, there's one other fact I wanted to mention too that's going to be important for this argument, is that here's a fact. The dual of the dual problem, what would you guys guess this has to be? Morally, what would this have to be? Somehow, if the world was just. It's the primal, right? It's going to have to be the primal problem. If I took the dual of this, which you can do, because we have two ways to do it now at least, you're going to end up back at this problem. So the dual of this dual problem is the primal. That's an important fact. And now let's apply Slater's condition. Applied to the problem P. Okay, applied to this first problem. And let's call F star to be the optimum here. And let's call G star to be the optimum here. Okay. So Slater's condition says that if I look at all the non-affine equality constraints, if I have a point that's feasible that satisfies those strictly, then I get strong duality. Okay, but there are no non-affine equality. There are no non-affine inequality constraints. All the inequality constraints are affine. So in fact, Slater's condition just reduces to saying if the problem is feasible, okay, then you get strong duality. Okay, so that's all that Slater's condition says. If P is feasible, then F star equals G star. Let's apply Slater's condition to the dual now. The dual is also an LP. Okay. If this is feasible, it's the same statement. If this is feasible, then we get strong duality, which means that G star is equal to the optimal value of its dual criterion, which is F star. Okay, so put together, we get strong duality in linear programs. And let's say strong duality fails only when both the primal and the dual are infeasible. So it's actually a challenge to construct such linear programs. They exist, okay, but it's not easy to construct them. It's, most linear programs that you try to construct that are obviously infeasible, they're not going to have an infeasible dual. So these exist, but they're actually a challenge to construct. And I think we gave you one on the homework. We gave you an example of them in homework, and you're going to just verify that it's primal and dual are infeasible. But it's only for those very pathological linear programs that we don't get strong duality. For all the other cases, according to Slater's condition, and this kind of clever idea of applying it both to P and also to D, because the dual of D was P, we saw that if either one is feasible, which is very, very weak, then we get strong duality. So the summary is that you could go forward thinking pretty much any LP you'll see, you have strong duality for that LP. Actually, no. So I'll repeat the question because I don't think everyone could hear. The question was, is this fact specific to linear programs? And it's actually not. And when I talk about duality and dual uses in 2 lectures, I think, I'll tell you for which problems that's true. But it actually is true for a lot of convex problems, for a very big class of convex problems. You can't really expect to get, there's no trial, there's no dual of the dual that's something like, I don't know, that's not the primal. It's usually the case that the dual of the dual is the primal. So a sufficient condition is that the problem's convex, let's say, and I think that if the inequality constraint functions are closed, I think that's good enough. And the criterion is closed, then it's good enough. But in a couple of lectures, we'll revisit that probably. Other questions? Okay. I wanted to go through the SVM dual, which is, I think, a big kind of topic of study in ML. At least classically, people spend a lot of time thinking about the SVM dual. And I think that duality and the KKT conditions are like the best way to understand SVMs. I would say something similar for lasso too. I mean, maybe the best way to understand them mechanically, not like statistically. It's like a very good thing to go through. And on the homework, I think we're going to have you implement the dual and the primal, or just call some kind of QP solver and check that you actually do get strong duality. So the SVM problem, let's just go ahead and write down the Lagrangian. With the problem being as stated on the slides, right? We have data x and y. I'm going to call the rows of x, x1 through xn. The SVM criterion is minimize 1/2 the norm of beta squared plus some tuning parameter c times the sum of these c variables. And we have inequality constraints on these variables, bigger than or equal to 0. And these are my margin, soft margin constraints. Yi, which is plus or minus 1, times xi transpose beta plus beta 0 is bigger than or equal to 1 minus ci. Okay, so this is a QP, right? If I look at all the constraints, they're all linear. This is a quadratic in my primal variables. And I'm going to define, let me write down the constraints for you. I have these constraints. So I'm going to define a dual variable wi for each one of these, and vi for each one of these. Okay, and the Lagrangian is just the criterion. And I'm going to subtract off the sum of these vi's, ci's, and I'm going to, let's say, add wi times, rearrange all this so this is something less than or equal to 0, and that something you'll see is 1 minus ci minus yi xi transpose beta plus beta 0. That's the Lagrangian. Okay. We can minimize this out over beta and beta 0 in order to get the Lagrange dual function. And the easiest way to do that is to just think of everything in vector form. So I'll just write this as 1/2 beta transpose beta. And I have, let's say, plus c minus, let's say, c times the 1's vector minus v. I'm going to collect all the terms that multiply c. And I'm also going to be subtracting off w times the 1's vector transpose c. And I'm going to now define, let's say, x to be a matrix, x tilde to be a matrix with rows, yi times xi. So xi were the rows of x, but x tilde I'm just going to multiply its rows by the sign of the corresponding class. It's going to make this a more convenient expression. And now if I look at just the linear term I have on beta, I just have, this should be x tilde transpose w quantity transpose beta. Okay, that's just combining this term, writing it in this notation. And I have a bunch of other terms. So the other terms I have left over are there's the quadratic bit that I have here. No, sorry, the quadratic bit is here. I guess the only other term I have left over is, it looks like probably the sum of the w's times beta 0. Is there any other appearance of beta 0? Oh, sorry. It's actually y. It's right. Y transpose the w's, right? Because the beta 0 is in the parentheses here. That's the Lagrangian. Okay. As I've written things in terms of matrices using vectors, it's just a quadratic. We've done the general quadratic minimization for deriving the dual of QPs on a previous slide. The same thing happens here. I just, let's say, differentiate with respect to beta 0 and c, set it equal to 0, see what values I get, plug it back in. Okay, so this just comes from straightforward calculation. That if I minimize out over my primal variables, my Lagrangian, I should expect to get a quadratic, just like I did before. And well, there are some cases we have to pay attention to here. If w transpose y was not 0, then I could make this minus infinity by taking beta to minus infinity, beta 0, right? So clearly that has to be a constraint. And if this thing, right, was not equal to 0, whatever multiplied c, then I would also be in trouble. W is a vector. Because I could take this to be minus infinity by taking c to be oriented in a certain direction. So it's minus infinity unless some constraints are met. And those constraints are that what we just said, W transpose Y has to be 0. And this thing has to be equal to 0, which we can write as W is equal to C1 minus V. Okay, and in this case, it's going to be a quadratic in W. This is going to come from the same type of calculation that we saw in a previous slide. Right, this quadratic just comes from minimizing this function with respect to beta. Okay, so the SVM dual is this problem. Okay, maximize overall W minus 1/2 W transpose X tilde transpose X tilde transpose plus 1 transpose W. There's still a variable V here, okay, which we can actually eliminate as part of this constraint and just write this as W must be between 0 and C in every component. It's a way of rewriting the constraint that W is non-negative in every component in this equality constraint after eliminating V, because V doesn't appear anywhere in the criterion. And this equality constraint we had from our minimization here, this is hopefully familiar to a bunch of people after taking 701. This is, for example, like in a very simple example, this is like the kernel matrix here. And this is a linear SVM. We haven't done any kernelization, but we would think of this as the kernel matrix in the SVM. So this is the SVM dual, and while Slater's condition says that if this primal problem had any nonlinear inequality constraints, then we'd have to have a feasible point that satisfies them strictly. But there are no nonlinear inequality constraints, so it's satisfied because it is feasible. That's all that we require. So we have strong duality, which means that this maximization and this minimization bring us to the same thing. And in fact, you might recall from SVM, what you know about SVMs, that at the solution, beta is equal to X tilde transpose W. So that we have an even kind of greater use of duality here, where it's not just that we can learn about the primal criterion value from the dual criterion value, we can actually learn about the primal solution from the dual solution. So that seems like actually a much more practical implication, right? We were talking about criterions values matching all along. I'm actually telling you that in SVMs, you can actually derive the primal solution from the dual solution. It's further than their criterions. And this is not a coincidence. It's actually a general fact, again, about duals that we're going to learn when we talk about the KKT conditions. And we'll revisit SVMs in the context of the KKT conditions, and we'll kind of learn a bunch of stuff about the dual as well. The only thing I wanted to say, I guess, quickly was that there's this quantity called the duality gap, which is if you have any primal feasible point X and any dual feasible point U and V, we can look at the difference between the primal and the dual criterions. That's called the duality gap. That's, first of all, it's always bigger than or equal to 0 by construction. Second of all, because this is always less than or equal to F star in every component, the duality gap actually upper bounds how far X is away from optimality. That just comes from the fact that this is less than or equal to F star in every component. So that means that if you're thinking about an algorithmic perspective, you could be trying to iteratively solve the primal and the dual, say by doing something like gradient descent, or we'll learn more complicated methods as we go throughout the course. And you could at any point, let's say, pause and say, let me record the difference in the primal criterion and the dual criterion. And assuming that you've stayed feasible, which most algorithms should, that is actually an upper bound on how far you're away from optimality. It's a super important practical implication of duality. Right? This is our first really rigorous way of, let's say, stopping an algorithm with a guarantee that we're close to the solution. It's by recording the duality gap. Okay, and we'll revisit that when we talk about interior point methods a bit later in the course. So it looks like I went right to the end of the course, even though I had only 20 slides. Apologies, I hope that it was at least thorough enough that you guys got a lot out of it. So I will see you guys on Monday.